In this lesson, we will use the TI-84 to determine the probability of a sum based upon the central limit theorem for sums, and also determine a sum given the number of standard deviations the sum is away from the mean of the sums. To begin, let's review the central limit theorem for sums. The central limit theorem for sums says if you keep drawing more and more samples of size n with a large enough n and taking their sums, these sums form their own distribution, the sampling distribution, which approaches a normal distribution as the sample size increases. The normal distribution has a mean equal to the original mean multiplied by the sample size, and a standard deviation equal to the original standard deviation multiplied by the square root of the sample size. So going back to our example, an unknown distribution has a mean of 90 and a standard deviation of 15. A sample of size 80 is drawn randomly from the population. Part A, we're asked to find the probability that the sum of the 80 values, or the total of the 80 values, is more than 7,500. We can indicate this as the probability that the sum of x is greater than 7,500. Before we determine this probability, let's find the mean or average of the sum of x as well as the standard deviation of the sum of x. So the mean of the sum of x is equal to the sample size times the mean of the original distribution, which is in this case 80 times 90, which is equal to 7,200, and the standard deviation of the sum of x is equal to the square root of n, which is the square root of the sample size. So we have the square root of 80 times the original standard deviation, or the standard deviation of x, which is 15. And let's go ahead and leave this as 15 square root 80, even though it could be simplified. And now we will use the normal CDF function on the TI-84 to determine the probability the sum of x is greater than 7,500. To begin, we press second vars for the distribution menu, option 2 for normal CDF. Now we enter the lower bound, upper bound, mu, and sigma. And this information is for the sums, not the original distribution. So because we have the sum of x greater than 7,500, the lower bound is 7,500. Enter. Need to exaggerate the upper bound. I'm going to use 999,999. Sometimes you'll also see scientific notation used, but this should be good enough. Enter. Mu is the mean of the sums, which is 7,200. And sigma is the standard deviation of the sums, which is 15 square root 80. Enter, enter, enter. And we have the probability to 4 decimal places. We have 0.0127, which is equal to 1.27%. Next, we're asked to find the probability the sum of the 80 values is between 7,100 and 7,300, which is the probability the sum of x is greater than 7,100 and less than 7,300. So going back to the calculator, second vars, option 2 for normal CDF. Now the lower bound is 7,100. Enter. The upper bound is 7,300. Enter. The mean and standard deviation the same. Enter, 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 and enter one more time. To 4 decimal places, we have 0.5439, which is equal to 54.39%. And for the last question, we're asked to find the sum that is 1.2 standard deviations below the mean of the sums. We're told to round to the 10th place value. So the sum we are looking for, the sum of x, is equal to the mean of the sum, which is 7,200. This is the expected value, plus the z-score, which is negative 1.2 because the sum is 1.2 standard deviations below the mean, times the standard deviation of the sums, which is 15 square root 80. And the same formula is given here below. And now we'll go to the calculator and get our decimal approximation. We have 7,200 plus negative 1.2 times 15 square root 80. Which of the tenths place value is 7,039.0. I hope you found this helpful.